Hello everyone and welcome, this is Federico. Today we'll be talking about this paper called Tempered Sigmoid Activations for Deep Learning with Differential Privacy by Nicholas Papernot, Abradeep Thakurta, Xuang Song, Steve Xian, and Ulfar Erlichsen by Google Brain. So first of all, let's deconstruct this title. Tempered Sigmoid Activations, well, we can already kind of infer that this will be some kind of activation function manipulation to work on this task, which is called differential privacy. Now, if you don't know what differential privacy is, it explains it quite straightforwardly in the abstract. So because learning involves sensitive data sometimes, machine learning algorithms have been extended to offer privacy for training data. And this is the idea with this GDPR movement and all these laws on data privacy, which are luckily being put out. We need also to make our algorithms kind of forget about some data, or maybe instead of forgetting, which is one aspect of where you can go about this, which is just retraining on the data, we can just make the data kind of obfuscated by adding some noise and stuff of that nature. In practice, this has been mostly an afterthought, but again, with privacy preserving models obtained by rerunning training with different optimizer, but using model architectures already performed well in a non-privacy preserving setting. So again, this is like a kind of a naive approach, but this approach leads to less than ideal privacy utility trade-offs, as we show here. So instead, what we propose is to kind of build these architectures around privacy, which is I guess a less expensive way of going about it. So one must bound as strictly as possible how individual training points can possibly affect model updates to guarantee this differential privacy. So in this paper, we observe that the choice of activation function is central, which is, it's quite, they make a pretty straightforward argument in this paper. It's quite nice though, and so we demonstrate how some activation functions, some family of activation functions, the tempered sigmoids, they outperform unbounded activation functions like ReLU. And then we'll get more into it. So first of all, let's kind of go over what this formalization of differential privacy is. So to reason about privacy guarantees of algorithms, or maybe let's look at the contributions. So firstly, with this point here, we show in section 3 how tempered sigmoids control the gradient norm explicitly, which we'll go over. Then they show how these tempered sigmoids are empirically superior over ReLU. And then the advanced state of the art. Okay, fair enough. It has to advance state of the art or else it won't get accepted. So again, if we want to formalize this differential privacy idea, so informally, an algorithm is differentially private if it always produces effectively the same output when applied to two input datasets that differ by only one record. So notice first of all that it's the algorithm that's differentially private. So it's kind of the method you're using is differentially private if this is the case, and then this is just more formally a learning algorithm A that trains models from the set S. So these are all sets of models that the algorithm is kind of optimizing. Is epsilon delta differentially private if the following holds for datasets D and D prime that differ by one record. So namely what we're doing is we're saying, okay, there's this epsilon, which is the privacy guarantee, and we want this bound to be as tight as possible. So that we want this this epsilon to give it to be as low as possible so that this bound is tight, right? Because obviously if epsilon is low, then this turns into a 1, right? So we want this bound to be as tight as possible on these two different data sets, okay? So we want to pretty much be the result on data sets which differ by only one record to be as close as possible. So and then there's some nice properties of differential privacy. So again, these are maybe a second thought, but in particular, the output of a differentially private algorithm can be arbitrarily post-processed without weakening of the guarantees. So that's quite useful in practice. And then if let's say an algorithm is epsilon differentially private, then if you have k training data records per person, then it will be k epsilon differential, and then this is, you can kind of figure it out just by this formalization, which is quite nice. So how do we do this? How do we actually go about this? Well, there's this differentially private stochastic gradient descent, DP-SGD, which is a method for training these networks. And the way it's done is you do the per example gradient, so you don't use a mini batch anymore. And then what you do is you clip these updates such that it only affects the sorry, I'm getting messages. It only affects by up to a factor of c, right? So maybe this is more clear. Our gradient is updated by the minimum of 1 or this factor here. So obviously here we're the bottom, the denominator is the L2 norm of the gradient, and then we are bounding it by c. So pretty much we're clipping we are restricting by how much this gradient can be updated. And the idea here is that we are kind of not allowing it to overfit too much on an update, because keep in mind that we're not doing any mini batches. This is for each training point. So we're clipping by how much each training point can affect the gradient. So that's the main idea. And the problem is, and then this is maybe what they talk about here, is that because this operation is performed on per example gradients, this allows DP-SGD to control the sensitivity of learning to individual training examples, which is what we were saying. However, obviously there's information loss, namely the information loss is this, let me get black, it's namely this, like the difference between this and this, right? Because you're just pretty much, if this is over 1, so if this is over 1, then the difference between the two is all lost information. So this is why, let's see, again, it will lead to information loss. One way to reduce the magnitude is to prevent the model's activation from exploding. Well, how do we do this? Now, ReLU is just looks like this, right? And more importantly here, this is unbounded. This goes on forever, right? So if this is unbounded, it means that this potential clipping can have a lot of information loss. And then this is where they are arguing that you lose performance. So how do we undo this? Is we introduce this family of functions called the tempered sigmoids, which are parameterized by a scaling factor, temperature, and offset. And then here you can see what they look like. And more importantly, if you set scaling to 2, temperature to 2, and offset to 1, which is this blue function here, then you get tanh. So that's quite elegant. And then I think one of the observations of this paper is that tanh is effectively the best performing one for some, which beats state-of-the-art differentially private models. So this is the idea. Then you can kind of tweak around with it. And then what they show, which is this part here, is that this temperature directly, maybe I'll just read it, but so controlling the gradient norm. So temperature, based on this intuition, we propose replacing, so the intuition of that, like tanh, or that ReLU kind of explodes. We decide to replace ReLU with tempered sigmoids. So there's an idea which is conceptually close to ours, the use of tempered losses, and this was shown to provide robustness to noise during training. Okay. Controlling the gradient norm. One of the main issues in practice with DP-SGD is tuning the value of the clipping parameter. If C is set too low, then clipping introduces bias by changing the underlying objective optimized during learning. Instead, if the clipping parameter is too high, clipping increases variance by forcing DP-SGD to add too much noise. Because DP-SGD, or I guess they discuss this here, recall that DP-SGD adds Gaussian noise with variance sigma squared to the average of the per example gradients. Again, this is to try to obfuscate these gradients. Anyway, this is, I guess, more kind of into the details of DP-SGD, which I'm not gonna get too much into, but the main idea here is that the gradient of this loss function is controlled by this temperature. So tweaking the temperature is what will actually kind of give you better differential privacy. Indeed, it turns out that the temperature parameter T in equation 3, which is the one of the tempered sigmoids, can be used as a knob to control the norm of the gradient of the loss function. And an appropriate choice avoids these two issues of clipping, which is again, and then here they extend it from a single variable loss function to a multivariable one. So this is all really quite a straightforward argument, but quite a nice one. And then here the benchmarks, or I guess the experiments, they run it from MNIST, Fashion MNIST, and CFAR10. And yeah, so here they're using convolutional networks. So all they're doing here, and I guess they outline it here, is literally changing the activation function, and they're saying this is better for differential privacy. And here we can, I think this is a plot for the accuracy so of the tempered sigmoids as a function of the scale and the inverse temperature and offset. So here you can see kind of some patterns of how the accuracy kind of seems to bunch up, which is very nice. As you can see, this is kind of hard to read, but it seems to bunch up here in the middle, and then it's kind of hard to make out what there is, but you can see that the scale, I guess more importantly, is that it's all in the same range, and that's obviously very good because it means you don't have to do as much like hyperparameter search, because obviously these ST and O's are hyperparameters again, so we want to try to minimize that. And then here they show what they were hinting at, is the fact that tanh, or tanch, I guess, which is again this it's this phi function. This phi function with parameters s. The scaling is 2, the temperature is 2, and the offset is 1. Does beat ReLU. So this is again very trivial change. Just saying, look, in this scenario, ReLU is better, is worse at privacy than tanch. Very simple argument. There is some intuition, and there's empirical evidence. So in Pacton, maybe let's just read this bit. To explain why a simple change of activation function has such a large positive impact, we conjecture that the bounded nature of a tanch, more generally tempered sigmoids, prevents activation functions from exploding. And again, this is just what they're saying. We don't want exploding grade, and then obviously this extends to stuff other than tanch and ReLU. We're just saying for differentially private problems, what we want. And then here there's the accuracy. They show that it's well, I guess it beats by quite a margin ReLU. They're just saying if we have an exploding function, something that like does not converge to a value, right? It has no limit. This won't work well for the simple reason that we need to bound this. We need to clip this this growth, and clipping obviously introduces loss of information. So this is the argument. This is the paper. I mean, I had to kind of go over it quite quickly, but simple argument. I really liked it, and yeah, hope you enjoyed the video. And if you did, feel free to share it and whatnot. And